All right, let's get into volcanoes. Okay, I couldn't see myself there for a second. All right, so volcanoes and plate boundaries. We talked about this before. Volcanoes occur at divergent plate boundaries where you're going to get that tension is the stress, remember that? Where it's pulling away. It's creating this weaker area in the middle there where it gets pulled away, and that provides an opportunity for magma to come up and create this volcanic mountain. It all depends on what's going on under the surface as well. You need magma to be able to create a volcano. And then we talk about convergent plate boundaries, and that's going to be like the ring of fire or the island arc. So that's usually when we get a subduction zone where that denser oceanic crust subducts, it goes under another piece of crust. It heats up underneath the surface, and then it's got to go somewhere, so it comes back up in a weakening of the crust and creates itself a volcano. So right here on these plates, these lines, these striations are going to be indicative of volcanic activity. So you see all around this Pacific plate where the ring of fire is, there's a lot of volcanic activity. And then you've got the island arc in here that creates more volcanic activity. So this is where the plate boundaries are. Here's a convergent plate boundary. We've got a divergent plate boundary here. So that's where we're going to get volcanic activity. The other way a volcano can form is due to a hotspot. And a hotspot has nothing to do with plate tectonics, really. It's just we've got like a weak spot in the crust, and then there's a lot of magma in the mantle that needs to come up. There's a spot in the mantle where it's just really pushing through hard, and that's going to be a hotspot. A good indication of a hotspot, or a good example of a hotspot, is going to be the Hawaiian Islands. So those islands are basically just big volcanic hotspots that formed and moved with plate tectonics and then cooled. And I'll show you right here. We've got the island of Kauai. This is going to be much older than the big island here. So Kauai eventually at some point in time was all the way over here over this hotspot. And with the motion of the Pacific plate going westward, it started moving west. And as it moved, it got weathered away due to, the ocean, wind, precipitation, all sorts of things. And so that's why it's smaller than the other islands. It's smaller because it's much, much older. This has a lot of dormant volcanoes because there's no magma activity going on in here. A lot of these Maui, Oahu, they don't have very much activity anymore. The Big Island, however, has a lot of activity because it is over the hotspot. So the Big Island is going to be the youngest island, and it's also the largest island. They call it the Big Island because it's the largest island. And it just hasn't had the chance to be weathered away quite yet. So we can expect within millions of years that Kauai will no longer be a thing, just due to weathering away and that motion of the plate tectonics moving away from the hotspot, which built the island in the first place. So magma versus lava, this is important to understand. So magma and lava are both molten rock, and they're both associated with volcanoes. The difference is magma is beneath the Earth's surface, okay? Remember that, magma beneath the Earth's surface, and lava is on the Earth's surface. So when you think of an explosive volcano, all of that molten rock is going to be lava coming out of the volcano. On the inside of the volcano, that's magma. So here's just a good example. Here's that lava on the surface. You can see it, you can touch it, don't touch it. And then we've got magma here. It's a big reservoir of molten rock underneath of the Earth's surface, and it gets pushed up to create these hot spots, and lava comes out of there. So let's look into the anatomy of a volcano. So on the inside of the volcano, we've got a magma chamber. That's on the bottom here. I'll go back. This is a magma chamber right here underneath the Earth's surface. So that magma chamber is going to eventually get filled up with magma, and plate tectonics is going to push and create energy to make it go upwards. And that magma is going to go up through the middle of a volcano through the pipe. It says conduit here, but just remember pipe. And then every time that magma escapes and comes out of the volcano to create lava is going to be a vent. So the top of the volcano is a vent. This area outside here is a vent. Anywhere that magma is able to escape the inside of the volcano and turn into lava is going to be a vent. And then we get lava flow just coming out of usually the crater here. The crater is kind of just like a hole in the top of a volcano. When it cools, they call it a caldera. So you're going to hear that word, but just know that the caldera is the cooled crater, and the crater is the hole that is created through magma activity coming out through a vent at the top of a volcano. So go ahead and just take a look at this volcano a little more in depth because there are going to be questions on the quiz about it. All right, so we've got a couple different kinds of eruptions with volcanoes. A lot of the time it's due to silica content. So with a quiet eruption, you're going to get a small amount of silica in the magma or in the lava, and you're going to see a lot of like slow lava flow. So quiet eruptions aren't that dangerous. You can tell when it's going to happen, and when it does happen, you can get away. The dangerous ones are going to be explosive eruptions, and those are going to be high in silica. The magma is high in silica or lava. And what happens with this explosive eruption is we get this pyroclastic flow, which is essentially just like a really, really fast release of hot gas. So if you are a volcanologist standing on the side of an active volcano and you know it's high in silica content, there's a much higher chance of you being incinerated by pyroclastic flow than if you were on a active volcano with a low silica content. And they know these things due to the mineral content. So pyroclastic flow, when that volcano has like some sort of eruptive quality, then this gas is going to be released. It's going to go down the mountain very, very quickly, and it's hundreds of degrees. So anything on that mountain face that is still there when the pyroclastic flow happens is incinerated. It's just gone. And you see this happening with a lot of like older civilizations that nestled up against explosive volcanoes. You see that there's human activity, and then there's a volcanic eruption, and then there's absolutely no activity right afterwards. And that's due to pyroclastic flow, and then also ash. So volcanic hazards are going to be pyroclastic flow, volcano bombs, which are just like large pieces of hot iron usually, but it's just like hot rock that gets shot out miles away and explodes. And then you've got ash. And ash is bad because not only does it go in the atmosphere and it cools down the atmosphere, causing strange climactic events, but it also will just kind of block out the sun. So a lot of vegetation's going to die in that area. A lot of the mammals around, or not even mammals, but just animals that breathe, are going to have trouble breathing because they're going to be inhaling gaseous mineral particles. So if you breathe in dust, it really hurts your lungs. So make sure you don't do that. But that's one of the hazards of volcanoes is ash and pyroclastic flow. You also get things like lahars, lava, which is like kind of like a muddy lava flow. Those are kind of slower with quiet eruptions. You're going to get lava flow, which is slow with quiet eruptions, and that's about it for volcanic hazards. In Hawaii, they have something called, I think it's called pahoho, which is just right here, this really slow-moving lava that eventually goes into the ocean and cools, that's a cool thing to look at. But here's an example of a quiet eruption with slow-moving lava. You can see it happening. There's not a lot of ash being displaced. It's not very explosive. So this isn't all that dangerous. But right here, we've got an example of a very explosive eruption here. So we've got a bunch of ash streaming into the atmosphere. This right here, this gas, is an indicator of pyroclastic flow. So right before this happened, a whole bunch of this gas escaped and went down the mountainside. And so pretty much everything on that side got incinerated. And then we're just going to get all this carbon dioxide. It's going to create an acidic environment in the air. And it's going to also release sulfur dioxide. So this is just all around not a very good thing to happen to the Earth. And then we've got some stages of volcanic activity. We've got active volcanoes, which means it has erupted recently and we expect it to erupt again within like 10 to a couple hundred years. Then we've got dormant, which it has not erupted in 200 years or so, but we expect it to erupt again in probably another couple hundred years or 1,000 years. And then we have extinct volcanoes, which they have not erupted for millions of years, and we do not expect them to erupt again. The magma chamber underneath of the Earth has solidified, so there's not much chance for that to escape and become lava. So here's just a good graphic. We've got an active volcano here. This magma chamber is completely full. It's pushing up. We're getting a lot of activity. We see a lot of like seismic activity, earthquakes. A lot of that plate tectonics is pushing this magma up, and you're going to get more eruptions. And then we've got a dormant volcano where it hasn't erupted in about 200 years, but we know that this magma chamber has been filling. It's been filling slowly. It's plugged up, but this can be reheated and turn into lava again. So we expect this one to erupt again, probably within like the next couple hundred to 1,000 years. This one's going to be, we're going to expect it within like 10 to a couple hundred years. A good example of a dormant volcano is the supervolcano in Yellowstone. I'm sure you all have heard something about it. We just have this huge magma chamber underneath of Yellowstone. It hasn't erupted for a long time, but we expect it to erupt again within a relatively soon future, like a couple hundred to 1,000 years. And then we've got extinct volcanoes, where this plug has completely covered the whole magma chamber. The chamber has no more magma. It's not filling up with anything. It's inactive. We don't expect any more activity from this volcano again. And so that should be just about all you need to know about volcanoes. I'm going to be posting a lab soon on this as well, so make sure you complete the lab because that's going to be 100 points. Other than that, go ahead and let me know if you want any more additional information on volcanoes, and let me know if you need any help. Otherwise, have a